spin up, as was introduced by James.
Great. Can people hear me okay? All right. Okay. All right. Okay. So, as James mentioned, he gave me the hard part we'll be talking about today, and that is how did the Milky Way spin up? And thank you, James, for introducing my work related to the transition from this spheroidal protogalaxy into the big disk phase, which I will be talking about today. I thought I already played. So, as was introduced yesterday by Vadim and also James just now, Gaia data has been used to reveal the kinematic structure of the Milky Way. Thank you to Vedant at Harvard for providing me with this data. So just to recap, this plots the circularity of stellar orbits versus their iron to hydrogen ratios. And a JZ by JC closer to 1 indicates the buildup of more aligned angular momentum or more disky. At the upper H is a rough proxy for stellar formation. And so you see over time the stars become more intense. So in particular from this plot, what we can extract from it is the evolution of the Milky Way's kinematic history and structure evolved in 3 distinct phases. Phase 1, an isotropic spheroidal protogalaxy, followed by phase 2, the protogalaxy spins up into a kinematically hot thick disk, and phase 3, the thick disk cools down into a thin disk. And I should also just mention that this data comes from actual observations of our Milky Way galaxy, but it turns out we can reproduce this result with fire data. So Fire 2 simulations can also produce these 3 kinematic phases of the Milky Way. On the right, we show a Milky Way analog simulated in a local group-like environment that forms a thin disk at redshift 0. So for the fire crowd out here, this is Romeo from the Elvis simulation suite, one of the Milky Way mass components in a local group pair. And the qualitative resemblance here is, undeniable. This Fire 2 simulated Milky Way mass galaxy run in a fully cosmological simulation also exhibits these 3 kinematic phases marked by transitions of spin up and cool. And it turns out that these 3 phases of protogalaxy, thick disk, and thin disk are ubiquitous in our Fire 2 simulation suite, 12 Milky Way mass halos, with all galaxies showing the same dramatic phase transitions of spin up and cool. For each halo, here we plot the median circularities distribution as a function of cosmic time using 2 methods, one of which I've called this archaeological method, which uses the stellar formation time and circularities of existing stars at redshift 0. So this would be like the median of the 3D histogram I've worked with previously. And then I've also used what I've dubbed the look-back method here in solid red. And this just uses the stars in the simulation snapshots corresponding to that volume time. This would be like a young stellar component at each 5-year period. So using this data, we have determined transition times for these 2 phase transitions corresponding to spin up and cool down for each of the simulations in our Milky Way. So here is visually these 3 phases. James showed this paper from Anna in his talk, and this is mentioned again. So we have our spheroidal protogalaxy which spins up into a hot thin disk and cools down a hot thick disk, and then cools down into a cold. So James talked to a large extent about this transition, and it corresponds, as was found in a series of studies, with the virialization of the inner surface active medium. But what about this transition? The initial spin up of the spheroidal protogalaxy into a hot sun. And this is what I will be introducing and talking about. So this is the transition that and just to give an idea of characteristic masses that spin up for each halo in our simulation suite, using the spin up primes that I found previously, I plotted that here. And spin up generally occurs around a virial mass of like 3 times 10 to the 11 solar masses, and stellar mass around 10 to the 10. And I should mention these are the Milky Way mass runs that are the Milky Way mass estimates. So a standard idea maybe is that this formation will start when there's enough stuff or mass. But what we see in this simulation suite is a pretty significant scatter by like a factor of 2, 3, or 4 in the masses at the time of spin. So another proposed idea is that the central concentration of the potential, or the concentration of the mass profile, central concentration of the mass profile, can trigger spin. And so this idea comes from Phil Hopkins, who led an extensive study using fire simulation. And if you're not familiar with this work, what he did basically in this study is he found a halo that ordinarily does not form a disk, and he ran the simulation up into a redshift of 1, and then he varied several different physics parameters to see what can promote a disk. And some of these tweaked parameters include varied cooling, radiative cooling and heating physics. He worked with feedback and star formation, and in particular, he also modified the potential. And what he concludes in this study is that the central concentration of the galaxy potential. So in this figure from his paper, he shows the present day rotation curves of a sample of fiery galaxies. And the peaky rotation curves in solid at least form a disk. While at redshift 0, I should mention this is at the present day, while the dotted lines do not form a disk. So after this study was completed, I decided to look into, instead of these sort of idealized numerical experiments, the more physical, realistic, fully cosmological zoom-in simulations and see how those compare. So what we find contrast to Hopkins et al. Is that the potential is least centrally concentrated at the time of spin. So what I've shown here is, this is Romeo again, the same test halo that I've been showing throughout this talk. I've shown its evolution of circularity on the top panel, and on the bottom panel, what we have is this quantity R peak over R90, which is the location of the rotation curve peak divided by the radius that encloses 90% of the young star. So this parameter, which I should mention Hopkins also used, measures the central concentration of the potential. The idea is that when the parameter falls below a value of unity, the potential is considered concentrated. And what we see here instead is that spin up occurs when the rotation curve is still rising throughout the galaxy. So here's spin up, here's this R peak over R90, and it's almost at a maximum around the time of spin up. In other words, unconcentrated. So we've extended this analysis from just the one Milky Way mass simulation to the full simulation suite we're working with. And here I've plotted the values of the rotation curve peaks for these 12 halos versus R90 at spin-up. So this is at the spin-up. And the idea is that when you lie above the dotted red line, the rotation curve is large with respect to, the rotation curve peak is large with respect to the size of the galaxy, and the galaxy is considered puffy. When you lie below that line, the galaxy is the potential is centrally concentrated. So it turns out that for almost all the galaxies in our suite, they're puffy and not centrally concentrated at the center. So if it's not the central concentration of the galaxy potential, what can it be? So one idea is that the galaxies at this stage in their evolution are far from equilibrium, and the potential is unstable before the disk. So a parameter that I've come up with to measure sort of this equilibrium is the centering of the baryon, the gas and stars throughout the disk. So this figure measures the evolution of the dark matter and baryon center of mass offsets from the total center of mass. So the dark matter is always pretty close to the center, while the baryons are moving around erratically, and the galaxy is not in a state of equilibrium until the baryons are well centered in the total potential, which I've marked by this purple. So what we see here is that once the baryons become well centered, the galaxy spins up. And for the full simulation suite, I've selected baryon centering times in this manner. So here is that for the full simulation suite. I plotted the baryon centering times versus the spin-up times. And what we see is that systematically, in all cases, the baryons center into the total center of mass before spin-up. To think about this physically for a minute, before the baryons are centered in the total potential, the system is out of equilibrium, and the early protogalaxy is highly chaotic and turbulent, and gas and stars can form these local centers that might destroy disks. And what we think is going on is that the system is not stable enough for a rotating disk to form until the baryons become coherent. And just some takeaways now, since I'm almost at time. The Milky Way's kinematic structure evolved in these three distinct phases, marked by a spheroidal isotropic protogalaxy, which spins up into a kinematically hot thick disk, which cools down into a cold thin disk. And we are required to Milky Way mass fully cosmological human simulations agree with actual observed data of the Milky Way through Gaia. The galaxy potential is maximally concentrated at spin-up, and baryons become well-centered in the potential before spin-up. That's everything. So, yes, they're maximally on. Yes, people are paying attention. That's good. Thank you.
Question? Yes.
Hi, great talk. I was wondering if you could sort of see this reproduced in galaxies with like really high merger rates, like M12W.
So yeah, M12W, yeah. That one, I believe, does not really form that much of a disk, so you don't see this, robust kind of three-phase kinematic structure. So I would say the answer is no, at least that, for the fire people here that know what M12W is, the answer is no.
Yeah, and just one quick second question. So you mentioned that the baryon center right before spin-up, and I don't know if the SIDM reruns have good enough snapshot cadence yet, but I was wondering, is that sort of affected if you implement self-interacting dark matter physics?
I can't say that I have a good answer for that. Yeah, it would definitely affect the offset of the dark matter centering. But how that interacts with baryons gravitationally. I don't have a good idea on it in this perspective.
Thank you.
Quick clarification. So is the claim here that the centering of the baryons causes the spin-up, or that the centering and the spin-up are two different features of the process of sort of this chaotic gas distribution settling down?
So they're two different features, but they're related in some sense. The centering of the baryons, I'm hoping, indicates that it's a measure basically of how far the system is from a sort of equilibrium and relaxed state. And the system has, like the galaxy has to form some kind of like equilibrium with its stellar and gas components before it can form a coherent disk that isn't subsequently destroyed. Does that answer?
All right, we'll do one more question while the next speaker sets up.
So is the time scale for the baryons to settle down in the center of mass just a dynamical time scale and things go as 1 over the square root of the density of the galaxy, or are there environmental effects? And
yeah. If we go back to that page, there's a large amount of scatter here, right? In terms of the time frame for. So in terms of a dynamical time, I'm not even sure if a dynamical time exists to speak of, or some kind of time offset between the baryon centering and spin-up occurring. However, what is clear, at least in this simulation suite, is that it is a necessary condition in that the baryon centered before the spin-up.
Okay, let's thank Olti once more.